The Constitution of India, Preamble. We, the people of India, having solemnly resolved to constitute India into a sovereign, socialist, secular, democratic republic and to secure to all its citizens justice, social, economic and political, liberty of thought, expression, belief, faith and worship, equality of status and of opportunity, and to promote among them all fraternity, assuring the dignity of the individual and the unity and integrity of the nation. In our Constituent Assembly, this 26th day of November 1949, do hereby adopt, enact and give to ourselves this Constitution.
Hello students, welcome back to the physics class. Hope you have understood the concepts taught in the previous class. Today we will be discussing yet another interesting topic in the chapter Magnetic Effects of Electric Current. The phenomena which we will learn today has a lot of applications in the modern world. Let us discuss in detail the magnetic field around a circular loop and a solenoid. In the previous class, we discussed on how to find out the magnetic field around a straight conductor, isn't it? How can we find out the magnetic field around a straight conductor? Yes, by right hand thumb rule or right hand screw rule. What is that right hand thumb rule? Imagine this is a conductor. Okay, how can you find out the magnetic field around this straight conductor? Or how can you explain right hand rule? You have studied, isn't it? Yes, suppose the current is flowing from this end to this end. That is, the current is flowing in the upward direction. How will you hold the conductor? You have to hold the conductor in your right hand. Okay, you have to hold the conductor in your right hand such that the thumb indicates the direction of current. Isn't it? Either direction current flow in that direction you have to hold your thumb. Okay, so the thumb represents the direction of current and the other fingers represents the direction of magnetic field. Okay, so here we can see the magnetic field is moving in the anti-clockwise direction. Suppose the current is flowing in the downward direction. So what happens? How will you hold the conductor? You have to hold the conductor like this, isn't it? And the other fingers encircling the conductor shows the direction of magnetic field. Okay, so here it is moving in the clockwise direction. Since this is how the clock moves. Okay, so I hope you have understood right hand rule. Okay, so today we will be learning how to find out the magnetic field around a circular loop. Okay, what is the direction of magnetic field inside the coil and how is it moving? All those things we will be discussing today. For that, we can do an activity. Okay? Yes, let us do an activity. Look at this arrangement. A conductor is made to pass through a sheet of paper in the shape of a coil. Okay. And the magnetic field lines at the two ends P and Q are marked. Okay. Can you see the magnetic field lines? At these two ends, here P and this is Q. At the two ends, the magnetic field lines are marked. Okay. And this is connected to a battery. And suppose the current is flowing in the clockwise direction. Okay, suppose the current is flowing in the clockwise direction. Is it clear? Look at the magnetic field lines inside the coil. The magnetic field lines inside the coil. Are they moving in the same direction? Yes. isn't it? It is moving away from us. അതായത് ഫീൽഡ് ലൈൻസ് നമ്മൾ നോക്കുമ്പോൾ നമ്മളിൽ നിന്നും എവേ ദൂരേക്ക് പോകുന്ന പോലെയാണ് നമുക്കത് ഫീൽ ചെയ്യണത്. ആണോ? ദാറ്റ് ഇസ് സെൻറ്ററിൽ നോക്കുക. ആരോ മാർക്സ് ദേ ആർ മൂവിങ് ഇൻ ദി സെയിം ഡയറക്ഷൻ, isn't it? Now, when the electric current passes in the clockwise direction, the magnetic field lines appear to move away from us into the coil. അല്ലേ? നമ്മളിൽ നിന്ന് കോയിലിനകത്തേക്ക് പോകുന്നത് പോലെയാണ് അതിൻ്റെ സെൻറ്റർ പാർട്ടിൽ കൂടിയിട്ട് എന്ത് പോകുന്നത്? മാഗ്നറ്റിക് ഫീൽഡ് ലൈൻസ് പോകുന്നത്. ഓക്കെ, are you getting me? That is, if the current is flowing in the clockwise direction, this arrow mark shows the current is moving in the clockwise direction, and you can see inside the coil, okay, inside the coil, the magnetic flux lines move away from us. Okay, now what I am going to do is, I am going to reverse the direction of current. Okay, suppose, now see, the current is moving in the anti-clockwise direction. Look at the magnetic field lines inside the coil. Yes, if the electric current passes in the anti-clockwise direction, the magnetic field lines appear to move out towards us. അല്ലേ? ആ കോയിലിൻ്റെ അകത്തുനിന്ന് നമ്മുടെ അടുത്തേക്ക് വരുന്ന പോലെയാണ് എന്ത് പോകുന്നത്? മാഗ്നറ്റിക് ഫീൽഡ് ലൈൻസ് പോകുന്നത്, isn't it? That is, if the electric current passes in the anti-clockwise direction, here that is moving in the anti-clockwise direction, so the magnetic field lines appear to move out towards us from the coil through its center. Okay, മനസ്സിലാവുന്നുണ്ടോ? അതേപോലെ ഇവിടെ ഒരു കണ്ടക്ടറാണ്. ഇതിന് പകരം നമ്മൾ എണ്ണം കൂട്ടുന്നതനുസരിച്ച് മാഗ്നറ്റിക് ഫ്ലക്സ് ലൈൻസിൻ്റെ എണ്ണം കൂടും. അതേപോലെ ഇഫ് യു ആർ ഇൻക്രീസിങ് ദ കറണ്ട്, ദ സ്ട്രെങ്ത് ഓഫ് മാഗ്നറ്റിക് ഫീൽഡ് ലൈൻസ് ക്യാൻ ബി ഇൻക്രീസ്ഡ്. ഇസ് ഇറ്റ് ക്ലിയർ? So, from this activity, you have found out that the magnetic flux lines inside the coil moves in the same direction, isn't it? And what is the second thing you have noticed? When the current is moving in the clockwise direction, the magnetic field inside the coil seems to move away from us, isn't it? And if the direction of current is reversed, that is, if the current moves in the anti-clockwise direction, what happens? The magnetic flux field lines seems to move towards us. Is it clear? So, next thing what we have learned is, what happens when you increase the strength of the current? Okay, or what happens to the magnetic field lines when we increase the strength of the current? Yes, as the strength of the current increases, the intensity of the magnetic field also increases. That is, we can see the number of field lines around that conductor increases. അതായത് നേരത്തെ ഒരു 4 ഫീൽഡ് ലൈൻസേ കണ്ടിട്ടുള്ളൂ എങ്കിൽ കറണ്ട് കൂട്ടുന്ന സമയത്ത് what will happen? 4ന് പകരം അതിനേക്കാട്ടിലും കൂടുതലായിരിക്കും ഫീൽഡ് ലൈൻസ് ഉണ്ടാവുക. Okay, so first thing is, how can you increase the strength of the magnetic field? First point we can tell, by increasing the strength of the current. Okay, second thing, instead of this single conductor, if you are increasing the number of turns, or അതിനെ ഒരു കണ്ടക്ടർ വരെ 1-2 കണ്ടക്ടറും കൂടി ഇട്ട് ചുറ്റി വെക്കുകയാണെന്നുണ്ടെങ്കിലോ, again the strength of the magnetic field can be increased. So is it clear? The magnetic field around a circular loop. Okay, now we will study the magnetic field around a solenoid. Okay, solenoid. Have you heard the word solenoid? So what is a solenoid? A long conducting wire wound in the form of a helix is a solenoid. Okay, and when current passes through the solenoid, what happens? It behaves like a magnet. Okay, only when current passes through that solenoid, it behaves like a magnet. So we can tell it is an electromagnet. അതായത് കറണ്ട് പാസ് ചെയ്യുന്ന സമയത്ത് മാത്രമാണ് അത് എന്തായി ആക്ട് ചെയ്യുക, മാഗ്നറ്റ് ആയിട്ട് ആക്ട് ചെയ്യുക. Is it clear? So what is a solenoid? A long conducting wire wound in the form of a helix. നമ്മുടെ സ്പ്രിംഗ് ഒക്കെ ഇല്ലേ, ആ സ്പ്രിംഗ് പോലെ ചുറ്റി വെച്ചിരിക്കുന്നതാണ് solenoid. The two ends of that solenoid will be connected to a battery. Okay, so when current passes through the solenoid, what happens? It behaves like a magnet. Okay, what is the peculiarity of a magnet? Yes, a magnet has two poles. One end will be north pole and the other end will be south pole. In the same way, when current passes through the solenoid, one end of the solenoid acts as the north pole and the other end acts as the south pole. Okay, but how will we know whether it is north pole or south pole?
X is a solenoid. Okay. Now this solenoid is connected to a battery through a switch. Okay. And nearby a magnetic needle is kept. Look at the deflection of the magnetic needle. It is aligned in the north-south direction. Okay. Now when the switch is on, see what happens? Current starts flowing through the solenoid and look at the deflection of the magnetic needle. The south pole is getting attracted and the pins are also getting attracted. South pole ആണ് ഇങ്ങോട്ട് ഡിഫ്ലക്റ്റ് ചെയ്ത് നിൽക്കുന്നത് അല്ലേ. സോ ക്യാൻ യു ടെൽ മീ വിച്ച് പോൾ വിൽ ബി ഫോം നിയർ ടു ദാറ്റ് മാഗ്നറ്റിക് നീഡിൽ? ഇറ്റ് ഈസ് ദി നോർത്ത് പോൾ ബിക്കോസ് അൺലൈക്ക് പോൾസ് അട്രാക്ട് ഈച്ച് അതർ. And look at the magnetic field lines around the solenoid. It is similar to a bar magnet, isn't it? And look at the direction of, or look at the magnetic field lines inside the solenoid. You can see uniform magnetic field inside the core, isn't it? Or the magnetic field lines are aligned in the same direction. Okay. And once it moves out of the solenoid, the strength of the magnetic field decreases. Is it clear? That is, a current carrying solenoid acts like a bar magnet. That is, one end of the solenoid will be north pole and the other end is south pole. Now what I am going to do is, we are going to reverse the direction of current. Okay, initially the south pole was getting attracted, isn't it? Okay, when we reverse the current, what happens? See to the deflection of the magnetic needle. Now the north pole is getting attracted. So which pole will be formed near to the magnetic needle? South pole. And the other end will be north pole. Understood? So this is one of the method to find out the direction of, or this is one of the method to find out the polarity of a solenoid. Now we can increase the strength of the current by adding one more battery. Okay, now two batteries are inserted into the are connected. When the switch is on, see to the deflection of the magnetic needle. Okay, yes, it deflects more and you can see more pins are attracted because the strength of that solenoid is more. So one method to increase the strength of the solenoid is by increasing the current. Next, what we are going to do is, we are going to increase the number of turns of the solenoid. Okay, again see to the deflection of the magnetic needle. Yes, the magnetic needle deflects more, isn't it? The north pole is getting attracted more. So which pole will be formed near to the magnetic needle? South pole. Now we are inserting a iron core inside the solenoid. Okay, so when the current is on, look at that deflection of the magnetic needle when the switch is on. Yes, it deflects more, isn't it? So the third method to increase the strength of the solenoid is using an soft iron core. Okay, more pins are getting attracted. Is it clear? The three methods to increase the strength of a solenoid. First one, increase the strength of current. Second one, increase the number of turns of the coil. And third one, insert a soft iron core. Okay, and see the number of flux lines increases. Let's see another method to find out the polarity of a solenoid. Okay, here when the current is on, current starts flowing through the solenoid, and look at the direction of the flow of current. Okay, it is moving in the anti-clockwise direction. Okay, so if the current is moving in the anti-clockwise direction, that end will be North Pole. Okay, that is why the North Pole gets repelled. Now we are reversing the current and see the current is flowing in the clockwise direction. So if the current is flowing in the clockwise direction, that end will be South Pole. See here. When the magnet is coming, the North Pole is getting attracted. So that end is South Pole. Is it clear? So like this way we can find out the polarity of a solenoid.
Now let us see the other method to find out the polarity of a solenoid. Okay, so here is the solenoid connected to a battery through a switch. When the switch is on, what happens when the switch is on? When the switch is on, current starts flowing through this solenoid, isn't it? So the direction of current is marked by arrow marks. Okay, so it is marked here. When I am standing here or from the point A, look at the direction of current. It is moving in this direction, isn't it? It is moving in this direction, that is, it is moving in the clockwise direction. Okay, so from this point A, when we look, what happens? The current is moving in the clockwise direction. It is moving in the clockwise direction. So we can tell if the current is moving in the clockwise direction, that end will be South Pole. Okay, if the direction of current is clockwise, that end will be South Pole. Okay, just see what happens when we go to the other end, B. Okay, just see what happens. Yes, from this point B, when we look, we can see the current is moving in the anti-clockwise direction. It is coming in the anti-clockwise direction, so the end will be North Pole. Is it clear? So, from this we can understand if the direction of current is clockwise, that end will be South Pole, and if the direction of current is anti-clockwise, that end will be North Pole. Okay, so this is how we can find out the polarity of a solenoid. Okay, now look at this figure. We can see the figure of a bar magnet and a solenoid, isn't it? So the first figure is the bar magnet, isn't it? The magnetic field around a bar magnet, and the second one, it is the magnetic field around a solenoid. So look at these two figures. We can see what happens inside these inside the bar magnet and the solenoid. The flux line seems to move in the same direction, isn't it? The magnetic flux lines inside the solenoid and the magnet moves in the same direction. Okay, both are identical, but what is the difference between that? In the case of a bar magnet, we can say the magnetism is permanent. Okay, so both are identical. Both means that bar magnet and the solenoid both are identical. But what we can see or we can discuss what are the differences between a bar magnet and a solenoid. Okay. In the case of a bar magnet, the magnetism is permanent. Okay, it's a permanent magnet. What about a solenoid? Is it a permanent magnet? No, it is a temporary magnet, or the magnetism is temporary. That is, only when current passes through the solenoid, it acts as a magnet. Is it clear? Then what is the next difference? Polarity. Tell me the case of polarity. Polarity of the bar magnet is permanent. Whether north pole and south pole will change? No. What about in the case of a solenoid? Polarity is temporary. That is, when you reverse the direction of current, what happens? The polarity of the solenoid also changes. Okay. And the third one is strength of a bar magnet is permanent. We cannot increase or decrease the strength of the magnet. Whereas in the case of a solenoid, the magnetism or the strength of the magnetism can be varied. That is, you can increase or decrease the strength of the solenoid. Isn't it? If you are increasing the electric current, or if you are increasing the number of cells, then now the strength of the magnetism also can be increased. Okay, so these are the differences between a bar magnet and a solenoid. Okay. Now, tell me what are the factors affecting the strength of a solenoid? Tell me. Yes, the first one. What is that? Number of turns of the coil. Okay, when you are increasing the number of turns, the strength of the magnetic field also increases, or the strength of the solenoid also increases. And the second one, what is that? Strength of the electric current. When you increase the current, strength of the solenoid also increases. So second one is strength of the current. Third one, area of cross section of the core. Area of cross section of the core. So again, I am repeating the factors affecting the strength of a solenoid. First one, number of turns. Second one, strength of the electric current. And the third one, area of cross section of the core. Okay, so tell me what all things we have discussed today. We have discussed on the magnetic field around a circular coil. Isn't it? That is, inside the coil, the flux line seems to be in the same direction. All those things we have discussed. Next, we have discussed about solenoid. What is a solenoid? It is a long conducting wire wound in the form of a helix. It is a temporary magnet. Isn't it? Only when current passes through the solenoid, it acts as a magnet. Then, on passing the current, what happens? The solenoid acts like a magnet and it has two poles, north pole and south pole. And how to find out the polarity of that solenoid? Okay, that is, if the current flows in the anti-clockwise direction, that end is north pole, and if the current flows in the clockwise direction, that end is south pole. And next is the factors affecting the strength of a solenoid. Three factors we have discussed. Number of turns, strength of the electric current, area of cross section of the core, and the differences between a bar magnet and a solenoid. Okay, so I hope you have understood the concepts taught in this class. If you are having any doubts, you can contact me. See you in the next class with a new topic. Bye.